Hello, this is a set of notes that reviews some of the main concepts that we talk about when we talk about atoms. So the first thing is there are different subatomic particles. Some of the later scientists realized this. And the three main particles that we talk about are protons, neutrons, and electrons. When we talk about the location in the atom, two of them are located at the nucleus. That's the protons and the neutrons. And the electrons are outside of the nucleus, going around on the outside. And so there are different ideas of this in the Bohr model and in the modern model, but both of them have electrons sort of on the outside there. The charge, by definition, we say that protons have a positive 1 charge, neutrons don't have a charge, they're neutral, and electrons are negative 1. And so when we're comparing charges, you have to remember that protons are positive and electrons are negative. I think if you think like pro is something that if you are pro something, it means you're in favor of it or you have a positive opinion of it or something like that. So pro, the prefix pro has something to do with positives or things like pros and cons, right? Electrons, then you're just going to have to remember that those are negative. There's not a very nice way of doing that, but electrons are negative, protons are positive. Also, there's an alliteration there between protons and positive, so if that will help you, whatever works. So we're going to talk about the mass next. The deal is a proton, normally speaking, is actually a very, very small number of kilograms. If you wrote it out in kilograms, it would be something like this. If you wrote it out in grams, it'd be basically the same number, but with 3 less zeros on it. So what we see here is that it doesn't make sense to talk about the mass of a proton in the normal units that we talk about mass in. Kilograms and grams are just way too large compared to the size of a proton. So we developed a new unit, which was based on carbon-12. Not super important that you understand what that means at this point, but what we decided was we said we're going to call the mass of one proton 1 AMU, or 1 atomic mass unit. All right, and neutrons have about the same mass. All right, so a proton is about 1 AMU, a neutron is about 1 AMU, and then electrons are much, much smaller. They're like 1/1800th of an AMU. And so for all practical purposes, we say that electrons essentially don't have a mass. Right, so these are some basic things about the subatomic particles that you're going to want to memorize. All right, where they are, what their relative charge is, what the relative mass is. All right, because you're just going to be expected to know that from this point on in this unit, and it's just the earlier you learn it, the more sense things will make. Okay, so here's something else. When Rutherford was looking at the atom, he found that it had this small positively charged nucleus, and when we say it's a small nucleus, we mean really, really small. All right, it's where most of the mass is because it's where the protons and the neutrons are, but it's very, very small in comparison to the rest of the size of the atom. And so there's this analogy with Carver-Hawkeye Arena. Imagine that you were standing at the half-court line in Carver-Hawkeye Arena and you were holding a marble in your hand. The marble would be equivalent to the size of the nucleus, and the entire arena would be the size of the atom. And so it's just this very, very small thing where most of the mass is in an atom at the center of it, and the rest of it is mostly empty space, and it contains these very, very low mass electrons. Another analogy that's given is if you think of the nucleus as a grape, the nearest electron is something like a mile away. All right, so that's where the electrons are on the outside and things like that. So when thinking about atoms, remember that the nucleus is very, very small and the rest of it's really large. When we draw pictures of atoms, when we use the Bohr representation, oftentimes we don't indicate this difference in size because it's not feasible to do that, but remember how small that nucleus is and that most of the mass is contained within that nucleus. Okay, this is probably the most important thing in this set of notes. What it is the atomic number, which is the number on the periodic table. That is the number of protons. And so when we talk about elements being different elements, carbon, nitrogen, oxygen, things like that, the thing that determines what an element is the number of protons it has. All right. Each element has its own unique number of protons, and so we can identify an element based on how many protons it has. So for example, if you look at lithium on the periodic table, it has a little 3 written above it. That 3 is the atomic number. All right. That is how many protons are in lithium. Sometimes we write it this other way, where the atomic number is written on the bottom. All right, and so just be familiar with both ways. This is what your periodic table looks like. This is what we call the atomic notation, or the isotope notation, or there are some different names for it. But in this case, the number is on the bottom, the atomic number is on the bottom. But it's how many protons there are in that substance. I tell this sort of goofy story. I say, imagine that you're an element, right, and you're speeding down the highway. If a cop pulled you over and asked you to identify yourself, what you'd show them is the number of protons, because that's like your identification. All right, so protons are super, super important. That's what determines what element is what. The mass number, all right, if you remember back to the mass, there are only two things in the atom that have a significant mass, the protons and the neutrons. The electrons, remember, are 1/1800th of that mass. So essentially, they're negligibly small. They're just so, so small. So when we find the mass of an atom, we look at its protons and neutrons. Because there should be a specific number of protons and neutrons in a number, it's not a decimal. Okay, it's got to be a positive integer. So in this case, the mass number is 7. We've got this other one. This is carbon-12. All right. The way, just to talk about how this is written, the way we write it out is we have a symbol for the element. We have the mass number written on the top left, and then we have the atomic number written on the bottom left. And then we would call this carbon-12 normally. And so if you write it out like this, carbon-12, and it's said carbon-12, and what that 12 indicates is the mass number. It's the number of protons and the neutrons together. We're going to do some practice here in a little bit, talking about how we can figure out how many protons and neutrons and electrons are in something, but that's how that works. So here, we've got some different elements. Should be on your handout. We've got aluminum, silicon, and calcium. If you look them up on the periodic table, you can find their atomic numbers. That's just the number of protons that they have. So you should see the column here that says atomic number matches the column that says protons. All right. The mass number, what we do is you look at the periodic table and there's a number written below it. I haven't talked about this yet, but that number is what's called the average atomic mass. If you take all the different kinds of an atom that exist out there and you average the mass, you get what's on the periodic table. We're going to talk about something called isotopes later on, but technically speaking, you can have atoms of the same element that have different masses. So you can have, we'll talk about in just a moment, hydrogen that has a mass of 1, or hydrogen that has a mass of 2, or hydrogen that has a mass of 3. And what's written on the periodic table is an average of all of those. So what we do is, if you're not given a mass of something, you assume that it's the most common of these different forms of the element, and you just round that number on the periodic table to the nearest. So if you look at aluminum, it's 26.9 approximately. That rounds to 27. All right, that's how that works. So getting the number of protons, that's as simple as looking at the atomic number. Then when we want to figure out how many neutrons there are in something, we take the mass number, and we know that protons and neutrons together make up the mass. All right, so in this case, there are 13 protons because it's aluminum. It's got a mass of 27 because that's what we round to from the periodic table. And then the remainder of that mass needs to be made up of neutrons, so we know there are 14 neutrons in this substance. We haven't talked much about electrons so far, but for all of these, you see the electrons are the same as the protons. It's because these are not charged particles. They're not what we call ions. And so for right now, we're going to assume that there's the same number of protons and electrons. But we'll change that up here in a little bit. So Dalton had this idea. He said all atoms of the same element are the same. What we've talked about here is how atoms of the same element have the same number of protons, but they can be different if they have a different number of electrons or neutrons. And so we're going to talk about both of those different cases here. So in this case, we're going to talk about protons and electrons. So there's something called an ion. An ion is a charged particle. All right, charge can be positive or negative. The way that this happens is an atom will gain or lose electrons. Remember, the protons and the neutrons are at the center. So those protons and neutrons are really hard to get at. The electrons are around the outside. So if an atom is going to lose something, it's going to be an electron. Or if it will gain something from another atom, it's going to be an electron. an ion that's positive is called a cation. There's a mnemonic for this. If you remember, like cats have paws, all right, like the cat's feet, right? So you would say that cations are positive, all right, and that will help you remember that they have a positive charge. If something has a positive charge, it doesn't gain extra protons, so that means it has to lose electrons to become positive. The opposite of this is called an anion. Anions have negative charges. All right, they get this by gaining extra electrons. Electrons are negative, so if they gain more of them, then the ion will become negative. And so in this way, by gaining or losing electrons, you see that we get atoms of the same element that are different in their charge. They have different numbers of electrons. But as long as they have the same protons, they're the same element. There's something called a polyatomic ion. I'm not going to talk too much about this right now, but what that comes from is when you have a lot of different atoms that are bonded together and they have overall a cumulative charge. But this will come up more later in the year, but not a super big deal right now. All right, on the back of your periodic table, there are a bunch of polyatomic ions. Hydronium and ammonium are a couple of them, but you also see like carbonate, right, and perchlorate and things like that. So there are some examples of these polyatomic ions on the back of your periodic table if you want to check that out. This is the key to the list of problems on the bottom of your worksheet. So you should have your worksheet in hand, hopefully, as you're looking through this. These are the answers to that worksheet. Go ahead, do it. Just check the key to make sure that you're getting them right. And if you have any questions on that, make sure you come in and ask. Okay, so now we're going to talk a little bit about charges here. So if we look at these, we can figure out how many protons they have based on their elements. All oxygens have 8 protons because oxygen is atomic number 8. All tins have 50 protons because tin is atomic number 50, etc., etc. Now what we have to do is think about what's going to happen to the electrons. With oxygen, it has a 2- charge. That means it has 2 extra electrons. Tin has a 2+ charge. That means it loses 2 of its electrons. Remember, nothing is going to be happening with the protons. All right. So in the end, when you do this process, you can compare the number of protons and electrons together. So oxygen has a -2 charge. It has 8 protons because it's oxygen. It's going to end up with 10 electrons because 10 negatives and 8 positives gives you a charge of -2. As for tin here, 50 protons, okay, it has a charge of +2. That means it has more protons than it has electrons. So it loses 2 of its electrons, and it has 48 in the end. All right, you can see a similar logic extended to these other two. If you have a question about that, again, come in and ask. Remember, anions are negatively charged and cations are positively charged. That's just a vocab thing that you need to be familiar with, so work on that as well. Okay, so we've talked about how electrons in atoms can be different, and that is what we call different ions. Now we're going to talk about what happens if the neutrons for an element are different. The word for that is isotope, and what that means is we have the same number of protons, so it's the same element, but it has a different number of neutrons, meaning that it has a different mass. So as an example here, there are 3 different forms of hydrogen. One is called protium, the second one is called deuterium, and the third one is called tritium. How these differ in their masses. You can see they all have atomic number 1. They all have 1 proton, but the mass number for these is 1, 2, and 3. And so hydrogen 1, protium, only has its proton. Hydrogen 2 has a proton and a neutron, and tritium, hydrogen 3, has a proton and 2 neutrons. And so these are all hydrogen, but they have different numbers of neutrons. We call those different isotopes of hydrogen. If you look at the periodic table for hydrogen, you'll see that the atomic mass for hydrogen listed on the periodic table is just about 1. All right. That indicates that this is probably the most common kind of hydrogen. So if you're looking at protium, deuterium, and tritium, protium is the most common type of hydrogen that exists. The commonness of an isotope in nature has to do with the stability of the nucleus. All right. What that means is if we're looking at these different kinds of hydrogen, the nucleus that has just 1 proton is more stable than a nucleus that has 1 proton and 1 neutron, and more stable than a nucleus that has 1 proton and 2 neutrons. The most stable nucleus here is just the form where there's just a single proton, and so that's the most abundant one. The deuterium and the tritium are actually slightly radioactive. They break down, they become hydrogen 1, and that's how that works. As another example of this, carbon, if you look at the periodic table, it's got 12.011. The most common isotope of carbon is carbon 12. There's other kinds out there, though. There's carbon 13, carbon 14, etc. If you look at lithium on the periodic table, it's 6.94. All right, 6.94 would round up to 7, so the most common type of lithium is lithium 7. Okay, now what we're going to do is a little practice just identifying the protons, neutrons, and electrons in some things. And so this first step is always to figure out how many protons something has. Magnesium has 12 protons because it's atomic number 12. So if you look up on the periodic table, if you look up magnesium, you should see number 12 next to it. That means 12 protons. All magnesiums have 12 protons. For the electrons, we look at the charge. This first one has a 2+ charge. That means there are 2 more protons than there are electrons. If there are 12 protons and there are 2 more protons than there are electrons, then that means there are 10 electrons. The way that we figure out how many neutrons there are is by looking at the mass. This says it's magnesium 24. Okay, magnesium 24 would have 12 protons because all magnesiums have 12 protons. But then it has to have a mass of 24. The neutrons make up the remainder of the mass. So that means there are 12 neutrons as well. For the mass on this one, it's the same. 12 protons, 12 neutrons to make up 24. For the electrons, the reason that there are 12 electrons in this one is it doesn't indicate a charge up here in the top right corner. That means it's a neutral atom, which means it has the same number of protons and electrons. Not all magnesiums have 12 electrons, but all magnesiums have 12 protons. If it's a neutral, not charged version of magnesium, it will have 12 electrons as well. We would call magnesium 2+ a cation because it's positively charged. And we call magnesium without a charge just a neutral atom. So the relationship between these two is that they are different ions of magnesium. They're the same isotope, but they're different ions. All right, here we have 2 different forms of carbon. Carbon has 6 protons because it's atomic number 6. Neither of these are charged, so they have the same number of electrons as they do protons, so that's why there are 6 electrons. The mass, however, is different for these, so there's going to be a different number of neutrons. The first one has a mass of 12, so that means there's 6 protons and 6 neutrons. The second one has a mass of 14. All right, if we're going to make up a mass of 14 and there are 6 protons, that means we're going to need 8 neutrons. These are both neutral, so we just call them neutral atoms. They're not ionic. And the relationship between these, they're the same ion, all right, but they're different isotopes because they have different masses. All right, so they're not charged. They're both just neutral atoms, but they have different isotopes of carbon because they have different masses, different numbers of neutrons. Using this logic, hopefully you can go through and fill out the rest of these blanks on the bottom half of the second page. So again, this is a key to those problems. If you want to pause the video and try that out and make sure that you're understanding them, that would be great. And then you can just ask me if there's anything else that you have a question over on those. There are a couple more of these. I'll just go ahead and show you the solutions. All right. These ones here, they're the same isotope because they're both sodium 22s, but they're different ions here because one of them is positively charged as a cation, the other one is neutral. So on this one, just make sure that you understand that, and if you don't, come in and ask me. And then we've got one more. This is chlorine. All right. This one here, they're both different isotopes because they have different masses, and one of them is an ion, the other one is a neutral atom, so they're different ions of chlorine as well. Okay, I believe that is it. So if you have any questions on this, make sure that you come in and see me as always, and just make sure these are some pretty fundamental ideas. So make sure that you review this set of notes and that you're pretty familiar with it.